Today we are going to talk about Lab 5 magnetic braking with Faraday roll. An introduction. Today's presentation is going to include Faraday's law, Lenz's law, Ohm's law, magnetic fields of a dipole, magnetic flux changing rate, and magnetic force on current loop. Here's the principles we need and how are the formula used. The first one is the electric fields formula, and second one is flux. The third one will be the flux change over time, which will equal to EMF. And the fifth is going to be derived from Ohm's law is going to be V equals to IR. So the current is going to equal to EMF divided by R. And the sixth is the force on the loop. And the seventh is the for gravity equal to mg, but also have to multiply by the factor J, which is the unit vector of y direction. And 8 and 9 are related, but they are mostly basically derived from Newton's law. The following are the experiments demonstration. There will be a tube, and then we'll put the magnets inside for it to fall through. And the tube is made of aluminum, which basically will cause the induced dipole so that it will affect the speed of magnet dropping. This part is an inner radius, and including the tube's thickness is outer radius. Here's the length of the tube, and this is the direction of the magnet's filling. And so as a default data, the length of the tube is going to be 0.27 meters, and width of the aluminum foil is going to be 0.02 meters. And the inner radius is going to be the 0.015 meter. As to outer radius, just going to be them adding together by the inner radius and the width of the aluminum foil. The mass of the magnets are 0.023 kilograms, and we're gonna use the magnets of a bar as mu, and we got the data from Lab 3, and the average times to fall through a tube is 12 seconds. Oh, here's the typo. Following our discussion question, why can't we use the PHYS tube, like for example, like the steel pipe? There will be way stronger induced magnets on the tube, which will slow down the dropping bar, which will slow the dropping bar down, which basically the magnets will be too strong, so that it will get stuck in the middle. What happens to the magnets? How does it compare to the magnets falling in free space without a tube? Falling into the free space is faster since there is way less interference on its way. And here we're gonna majorly use coding to solve the problem in this lab. And we can see from the code that this is the constant u over 4 pi, which basically 10 to the -7th. And resistitivities and gravity, they're all the constants. And following part, this part is the default data we have previously. The following are the defaulted code for creating the tube showing in the diagrams. And this following part is also the default value we have earlier on. And this is the initial locations of the magnets, which basically we set the starting points as 0. This function, as you can see, is calculating the dipole for this, from these two variables. So this one is the magnitudes and R has the directions. So basically we are using the formula right here, we just mentioned earlier on for the magnetic fields formula. This function is calculating the flux so that we can get the EMF so that we could know the induced current. And then we basically put this formula and then put it inside the function. Due to the fact that the formula is too long, so we separated it into numerator and denominators so that we could more easily to type it out. The following part is while loop. It's basically the most important part. This part is the positions of the magnets as they're falling off. They chop it into really time interval so that it could analyze every small situations. And as to this following part, basically they counted the tube as a little ring and it accumulated together became a tube so that we could calculate each ring's induced current and then calculate the force that add on the magnets. And then there's only two forces on the magnets. Basically, what we consider is the magnitude force and the gravitational force. So every point the gravitational force is the same. So when you put the rings, when you calculate each rings, you have to put it to add the magnitude force and gravitational force together. As to these two color, basically they're just manifesting the different direction, like counterclockwise and clockwise of the induced current. And then this part is just basically adding them together. And following part, they're using the vector to find the final positions and final speeds for the magnets. And this will be what you got from the program. This is when the magnets was dropping down the tubes. According to a code, the average time is about 12 seconds. Basically, we got the graph look like this. They will have the really flat times in the middle. Discussion question. There will be totally 4 discussion questions from the Canvas. The first one, the intensity of the color on the tube indicates the magnitude of current flowing through each ring. Red and blue indicates current flow in opposite directions. Which color respond to which? According to Lenz's law, you can tell red is correspond to the counterclockwise and the blue is correspond to the clockwise. What happened to the dynamics of the system when you flip the magnets around? Due to the fact that the aluminum tube initially does not have any magnetic dipoles inside, so it will basically doesn't have the really big effect. The current one is the version that will slow the magnet down according to the magnetic field created when falling, but it's induced current, so even when we flip it over, the magnet will still be slowed down by the tube. But the only thing that's going to be different is like the induced current is going to be the opposite directions. The third one, how does the total time into of your real world system compare to that of your computational system? How might the computational system be made more accurate? The time in computational is shorter. Um, so basically we have two factors. We have two arrows. It's a real world extra force and extra like condition that we have to think about. And the second one is just computational arrow. We should take the ear drag friction into account. Also, when doing the computational system, we could make the DT closer to 0, so we'll have more rings. Basically means that splitting the tubes into more like smaller pieces so that the time will be more accurate. Fourth, what does the shape of velocity versus time plot tell you about the force acting on the bar? When velocity equal the same, basically gravitational force will equal to the magnetic field force according to the Newton's law that when there's no external force acting on it, the speed will remain the same. But at the beginning and at the end, the force was not balanced, so that the force could be changing drastically, as you see. What if problem? What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamic of the falling magnet change? The magnetic force will increase until almost equals to gravitational force. Then the magnet would actually stuck in the tube, would not be able to fall down. Second, what if the holes or slots were cut into the tubes? Like, how would this affect the rings current in your model? The part will not have the current. Like, no magnetic force or less magnetic force will be on the hole, so that at this part, gravitational force will be the only force acting on a magnetic force on a magnet, so that it will the acceleration should be directly going down at the moment when it's facing the holes.